Okay, so we will start now with the first.
You can put in full screen.
I will put it just after I
Okay.
stop. Sorry. We will start with the first presentation. The first presentation is called Remarks on the Viatory Sequence and Corresponding Convolution Formulas. And it's a joint work from, will you present it? It's a lot of people, so I think that they will introduce themselves. Let me share the screen and full screen mode. Okay, we're ready to start. Okay. Please keep in mind that.
Okay, thank you. Good afternoon, boa tarde, and kalispera. In my talk, I will focus on the special sequence of rational numbers, which plays an important role in analysis, real analysis, complex analysis, and even hypercomplex analysis. This is a joint work with Isabel Cação and Helmut Malonek from the University of Aveiro, Graça Tomás from Polytechnic of Guarda, and Fernando Miranda from the University of Minho. So this is the plan for my talk. First of all, I would like to give a motivation and explain the context where this sequence appears. Then I will show some alternative definition of the Viatory sequence. Most of these alternative definitions are quite easy to prove that are equivalent, but I think it's worth to have a place with all the definition together. Then I will show you some properties. And finally, I will end with the convolution of the sequence and the corresponding convolution triangle. If the time allows, I will talk a little bit about the generalized Viatory sequence. So let's start with the motivation. The name of the sequence comes from a well-known Austrian mathematician, Leopold Viatorius, that lives, as you can see, for a long time and work for a long time. Is quite famous from his work on algebraic topology, especially on the Meyer-Viatory sequence, which has nothing to do with what I'm going to talk about. He also gave important contributions on functional and differential equations, on probability, and on positive trigonometric sums, and our sequence comes exactly from this field. So what he had proved is that he considered a sequence of numbers where the even order term are equal to the following odd term, and the even order term are related with the central binomial coefficients by this way here. This can be seen as a weighted central binomial coefficient, and he proved in this work that these sums here are positive. This has important consequences in complex analysis and defining univalent functions and so on, but in our context, they are important in another way. So the first terms of this week is this sequence. The sequence that Viatory is defining in this work are here. You can see that they are pairwise equal, but the context that comes from our work is not this, is the hypercomplex context. Let me just give some basic definition. We are considering an orthonormal basis of the Euclidean vector space, Rn, and here we have the usual multiplication rule, and this non-commutative product generates the 2n-dimensional Clifford algebra, CL0n. These elements A1, AN, A2, AN are usually called imaginary units or generators of the Clifford algebra. For the particular cases where n is equal to 1, we have just one generator, and if we
identify this generator with the imaginary complex unit, then we can see that the Clifford algebra CL01 is isomorphic to the complex numbers. And in the case that is more important here is the case of n equal to 2. We have the four-dimensional algebra spanned by these elements, 1, A1, A2, A1 times A2. If we identify this A1 with I, A2 with J, and this product with K, we end up with the well-known Hamilton quaternion algebra. In the hypercomplex context, this sequence appeared a long time ago, in 2007, because we were interested in defining special homogeneous holomorphic polynomials with respect to the hypercomplex variable x and its conjugate, so that these kind of polynomials behave like the monomials functions in the complex case. And our interest was in constructing special holomorphic functions as a series of this form. At that time, we are not able to solve the problem for general or for arbitrary n, but we end up with the solution with the case n equals to 2. This is the quaternionic case, and we were able to prove that the polynomial that we were looking for could be written in this form here. We have the hypercomplex variable x and its conjugate, and here are the numbers that we found they have to have this form here. We noticed that this polynomial, if you want to write this polynomial not in terms of the variables x and the conjugate, but in terms of the real part of the variable and the vector part of the variable, then these polynomials can be written in this form here, and this is the sequence given by this expression here. You can see that the first terms of the sequence, you can see if you compare with the sequence that Viatoris used in his result about the positive of the trigonometric series, it's a subsequence of that series without the first term. So we have the first term is 1, and then we have the terms pairwise equal. So we decided that although this is just a subsequence, we have coined this sequence with the Viatoris name. So now what I'm going to show you is several different ways of representing this sequence, what we have called the Viatoris sequence. Most of the representation, which are of course equivalent, are trivial to prove, and that some of them are not so trivial as that, but I'm not going to show here the proofs. The proofs are in the paper if someone wants to are interested and can see there the proof. So this is a way of representing the Viatoris sequence in terms of the binomial coefficients. This is the part that we were very interested on at that time, 2007, because we can write the Viatoris sequence in terms of generators of the quaternion algebra in this way. Here we have a new operation, which is called the symmetric product. And here are the symmetric powers, which are defined in this way. They can be easily computed. This operation now, this symmetric product is commutative, but it is not associative. So it's easy, but it is easy to compute this power symmetric powers, and the Viatoris sequence are given by the inverse of this sum. So this is another way of representing the Viatoris sequence. It can also be represented in terms of the double factorial, in terms of recursive
representation, where we can see easily that the terms of order, of even order, are equal to the terms of even order that precede this one. Can also be written in terms of the Bockhammer symbol. I have all this representation because depending on the subject, where depending on the way you are the tools that you are using to prove some properties, some of them appear in terms of the double factorial or in terms of the Bockhammer factorial, but it is trivial to prove that all these definitions are equivalent. In terms of the gamma function, of course, this is just for curiosity. It can also be written in terms of the famous Wallis integral. They are linked to Catalan numbers. The Catalan numbers, we have here the definition of Catalan numbers. They are also a kind of weighted central binomial coefficients, different, but in the case of the Catalan numbers, you don't have the pairwise equality. But we can also have this relation between the Vietoris numbers and the Catalan numbers. They are also linked to Legendre polynomials, not Legendre polynomials, but the value of the Legendre polynomials at the origin, and also with the Bessel function of the first kind, the derivatives of the Bessel functions of the first kind. So these are equivalent definitions. You can use the definition that you want depending on what you want to prove. You can also obtain other properties very easily. You can have an alternate series. This is equal to 1. You have a combinatorial identity, trigonometric identities. Now you don't have the positive of the series similar to what Vietoris had, because now you don't have the first term, so it's not possible to have the positive of both series, just one of them. Here some recurrence relation. And now it's important I have already said that they are a kind of weighted central binomial coefficient. So here we have Pascal triangle, we have here in orange the central binomial coefficients. We have also what in the literature sometimes appears as complete central binomial coefficients, which instead of have this, we have for all k, this is the floor function. So they are different, of course. If you go there, you have here, if you go to terms, you have the central binomial coefficient, of course. And here is the relation between the Vietoris sequence, the complete central binomial coefficient, and you also have, because it is also important to consider a subsequence of the Vietoris sequence, the sequence of the even order terms, which are related to the central binomial coefficient by this way. This is important because we are going to study some convolution of this sequence. The even order term of the Vietoris sequence also has important properties which can be derived very easily. We have in this link here a mathematical notebook where the proofs are of this formula. We have a lot of more identities are done by using the symbolic capabilities of the mathematics. Let me now talk about generating function of the sequence, the Vietoris sequence, and the even order term Vietoris sequence. In our work, we are especially interested in the ordinary generating function and exponential generating function. You have here the ordinary, the generating function For the Vietore sequence, this is for even order terms. Here you have the exponential generative functions. These are the modified Bessel functions. Okay, so this is important because I'm going to talk now about something new, which are the convolution triangles that arise when you do the convolution of the Vietore sequence and the even order term. So the convolution of the sequence, I think that you know what it is. We have here the definition of the K convolution sequence given in this way here. This is given a recursive definition. But what is important is the link between the convolution of a sequence and its generating function. Because if you know the generating function of a sequence, then the generating function of the K convolution of the sequence is obtained very easily. It's just to compute the generating function of the sequence to the power of K plus 1. For example, I'm going to show you here, in the case of the Vietore sequence, this is the generating function of the Vietore sequence. If you expand this sequence, we have this this function. You have here in I don't know what is the color, the red. You have here exactly the Vietore sequence. Now the first convolution is just to compute this generating function to the power of 2. The corresponding coefficients are the first convolution of the sequence. For the second one, you have here, you have to compute, but with any algebraic system, you obtain very easily the coefficients of the series expansion. So these coefficients in blue are the second convolution of the Vietore sequence. You can dispose these numbers in a table. Here we have the original Vietore sequence. Here you have the first convolution, the second convolution, and so on. This is for the Vietore's convolution. This is called the Vietore's convolution triangle, although this does not look like very much with a triangle, but we say this is the rectangle form of the Vietore's triangle. But if we move this row one position down, and this 2 and this 3, now we have what we call the left justifying triangle, and this now looks like a triangle, although in our work it's more convenient to use the rectangular form of the triangle. If you, instead of using the Vietore sequence, we use the even order term Vietore sequence, then we can compare with the triangle that we have. We can also compute the complete central binomial coefficient triangle exactly in the same way. You have this here. And we can compare now the Vietore's convolution triangle with the complete central binomial coefficient triangle. And you can see here that these are the scale. If you multiply this line by this number, you will obtain the corresponding line of the central binomial coefficient triangle. This means that the lines in this triangle are equal to the number of lines minus 1 times the lines here. You can also obtain the same result by observing that the generating function of the complete central binomial coefficient is related to the generating function of the Vietore sequence in this way here. So the same can be made for the even term. And now if you denote by, if we consider the matrix corresponding to that infinite array, then we can prove that the determinant of the matrix containing the central binomial coefficients the determinant is equal to this number, and the determinant of the matrix containing the complete center binomial coefficient is equal to 1. And we can use this to obtain this interesting equality, which says that the determinant of the Vietoris matrix is equal to the determinant of the even term Vietoris number. For example, in the case of considering a matrix of order 4, we have this result here. So I think that just one, I have 15 seconds. So let me just say that another property that we can see, and it's also easy to prove, this is the convolution triangle of the even order term Vietoris coefficient. And you can see that if you look at you can look here, and you can observe that you obtain the Pascal triangle in rectangle form. This is easy to prove, but it's interesting. Let me just say that if you want 2 minutes, okay, thank you. That now we know how to solve the problem. In 2007, we were not able to prove what were the results in the general case, but now, of course, that was some time ago. Now we know how to obtain the solution for our problem for any dimension n, and here we have the result. The sequence has to be of this form, or if you want, the first term of this sequence are given in this way. If n is equal to 1, the n is equal to 1 corresponds to the case of complex numbers, so all coefficients are equal because you have the complex power. When n is equal to 2, we have what I have already shown you, the case of the Vietoris sequence. The case of n equal to 3 is not very interesting. You just have the inverse of the odd numbers, pairwise equal, of course, because this is so what we think is that the most interesting case are the cases where n is even. So we have several results, but I think that I will stop here. This is the definition of the Vietoris sequence, generalized Vietoris sequence in terms of the binomial coefficient. Okay, thank you very much for that.
Okay. So, I don't know. If there are any questions, are there any questions here? Maybe? No, right? Okay. Then we will go for our next presentation with the title, a two-step quaternionic root finding method. Okay, these are some tough words. Okay. Okay. And we keep sharing like that. You can start.
Good afternoon. I'm talking about a two-step quaternion root finding method. This is a joint work with Maria Irene Falcão, last speaker, Ricardo Severino, next speaker, and Maria Joana Soares, that is here in the room but will not speak. Well, I'll start recording, remember some generalities about the algebra of real quaternions, H. This vector, sorry? Okay. H is a vector space with dimensions 4, with this basis where 1 is the real unity and I, j, and k are the imaginary units. The multiplication rules are defined by these identities. So a quaternion is an object with this aspect, with where Q note we usually denote by the real part, and in blue is the vector part that we usually represent by Q underbar. The conjugate of the quaternion Q is represented by Q bar, and is the same as in the complex case. The norm is defined this way, and any non-zero quaternion has an inverse defined this way. So we also define in H an equivalence relation, where two quaternions Q and Q prime are equivalent if and only if there exists a quaternion H such that Q prime can be obtained this way. This equivalence class define this equivalence relation define a class of equivalence, and it is formed by all the quaternions that has the same real part of of Q and the same norm of Q. If Q is a real number, then the conjugacy class is a singular set. But if Q is not real, then the conjugacy class is a sphere. Is a sphere in the hyperplane defined this way. So I will now talk about the ring of left one-sided polynomials. So we have a polynomial P where all the coefficients are localized in the left-hand side of the powers. This is a ring if we use the addition and multiplication as in the commutative case. The conjugate of a polynomial Q is defined this way, conjugating the coefficients, and we call the characteristic polynomial associated to a quaternion Q the polynomial psi of Q. It's a second-degree polynomial, and it is real. The evaluation map. So if we want to evaluate the polynomial P at Q, then we do it as in the standard way. But let me observe that the factoring, if we made the factorization of the polynomial, this operation does not preserve the evaluation. If we have a polynomial if a polynomial is a multiplication of a left-hand polynomial with a right-hand side polynomial, then in general, these two expression does not evaluate the same. So if we want to evaluate a factorized polynomial, we have to adjust the evaluation of the left-hand side polynomial in this way, evaluating the Q tilde, where Q tilde is defined as this way. The zeros of polynomial P. We say that Q is a zero of P if obviously P of Q is zero. If we call that we say that Q is an isolated zero of P if it is the only zero of the polynomial in the conjugacy class of Q. If it is not an isolated zero, then we call it the spherical zero, and all the elements of the sphere, the conjugacy class of Q, are all of them are also zeros of the polynomial. If all the real zeros of a polynomial are isolated, and if Q is a non-real spherical zero, this is equivalent to observe that Q and the conjugate of Q are both zeros of the polynomial P. If we have a polynomial P, and if we know that Q is the zero of P, then we can factorize the polynomial P this way. This means that Q is also a factor of the polynomial. And observe that any non-zero polynomial Q, if it is a spherical zero, then we can factorize the polynomial using the characteristic polynomial associated with Q. All the polynomial P has always a factorization with this aspect, where x1, etc., xn are not, in general, the zeros of the polynomial P. They are what we call the factors of P. If we want to recover the zeros starting from the factor terms, then we have to apply this formula here. In 2018, myself and the co-authors of this presentation presented a method. We call it a quaternionic Weierstrass method to compute all the zeros of the n-degree polynomial. The scheme is described this way. I don't start with some details, but where the polynomials L and R are defined here. We have also proved in that paper that if all the zeros of the polynomial are simple, and if the initial guesses are sufficiently close to the zeros or the factor terms of the polynomials, then the sequence generated by the method converges quadratically to the factor terms, and equivalently we prove that the sequence of zeros also converge to the zeros of the polynomial. So, in this talk, what we propose is a new method that we call it a two-step quaternion Weierstrass method, and the objective of this method is to accelerate the convergence of the method. In general, these methods, based on the Weierstrass correction, use the derivatives of the polynomial. So we in this case, as we have not, we do not compute the derivatives, we proposed a multi-step method that. Okay, let me show that. We can the start point was a well-known two-step Newton method that is described by this scheme. But here we use the derivatives of the polynomial. So we replaced the derivatives of the polynomials by the Weierstrass correction term that we present or we proposed in the paper mentioned some time ago, and we obtain, in this case, an iterative, two-step iterative scheme described by this. Okay. So, what we prove? We prove that if all the zeros are simple and the initial gases are sufficiently close to the factor terms, the sequence generated by this scheme converge with cubic order of convergence. The proof, we proved this statement, and the proof basically is made by induction on the order on the degree of the polynomial, and the details can be seen in the paper associated with this talk. The iterative scheme produces the factor terms, and obviously we can obtain the sequence of the roots applying the usual way to pass from the factor terms to the zeros of the polynomial. And also it is we observe that this sequence, the sequence of of zeros, approximating zeros, converge cubically with the order 3 to the zeros of the polynomial. So I will now present some numerical examples. These examples we use the mathematical package quaternion analysis and also a notebook that we call Q polynomial. All of these tools are available and the web address can be found in the paper associated with this talk. So, to evaluate the quality of the approximations, we use the way of compute the error of each iteration this way, okay, and we use this quotient to evaluate the local order of the convergence of the method. So, example 1, we start with a polynomial of degree 3 with factor terms. This one are these factors which correspond to these roots. So what we observed that starting with this sequence, we obtain the precision 10 power minus 16 after 12 iterations if we use the I will call the classical quaternionic Weierstrass method, and if we use the new method, two-step quaternionic Weierstrass method, we obtain the error after only 7 iterations. Here is the results of the computation. If we use a polynomial of degree 6, this one, then we obtain the precision 10 minus 16 after 22 iteration, start using the quaternionic Weierstrass method, and after 15 iterations if we use the new two-step methods. Okay, here are the results. Now, in this example, we use a polynomial of 3/4 and with 2 isolated zeros and with a sphere of zeros. We proposed in the last year a deflection algorithm that can be used associated with quaternionic Weierstrass methods that allows to obtain quadratic order of convergence for isolated and spherical rules. Observe that if the polynomial has spherical roots, we are not in the hypothesis of the theorem. But this deflection algorithm allows to recover the order of precision, 2 in this case. In this example, what we did, we applied exactly the two techniques, the deflection methods associated with the two-step Weierstrass method, and we observed that with and without this strategy, we obtain different results. So, if we use the Weierstrass quaternion method and the two steps, the errors of we never achieved in this case sorry. Okay, but now if we try to go to a more ambitious polynomial, if we multiply the last polynomial p by these two terms, which means that we are adding to the polynomial p two isolated zeros and a spherical zero, spherical zero, I, then we observe that if we use the deflection procedure with initial approximation, this one, we obtain after 9 iterations, if we use the two-step quaternionic Weierstrass methods, the tolerance that we impose. And here in this table, we can see a summary of these results. Some conclusions to end. What we, in this work, we derived a two-step method based on the Weierstrass method proposed by in 2018 for computed roots of a quaternion polynomial, and we have proved that with this method we obtain a cubic order of convergence. We also modified this two-step version of the method in a way that we can apply the method with two polynomials with spherical roots, applying the deflection technique that we proposed in the past. We hope it is possible to modify the scheme in order to improve its efficiency, in particular in what concerns to the number of evaluation required in each iteration. We intend to, but this is obviously future work. Some reference, and that's all. Thank you for your attention. Yes.
Okay. Thank you. So, are there any questions? Okay. So we will continue with our next presentation. And okay. This is our next presentation. Okay. The next presentation, the name is the stability of complex dynamics for two families of Cocciolerionic quadratic polynomials. After this, I have to find out what this is. Okay. Okay. Okay, you can start now.
Kalispera, everyone. My name is Ricardo Severino, and I'm going to talk about some work that we have done, a bunch of people from the University of Minho in Braga, Portugal, Maria Irene Falcão, Fernando Miranda, and Maria Joana Soares. Thank you. Our work is about dynamical systems. Dynamical systems is done in the context of co-quaternionic scheme. And let me say a few words about what was in the origin of this work. Let me just say a few words about complex dynamical systems. It's known that complex quadratic polynomials exhibits the same. That all complex quadratic polynomials are equivalent, and although it is a very, very satisfying property, we can say that there is also some feeling that this is also a limitation in terms of diversity, in the sense that we have only one family of maps, and of course, although it has some beautiful properties, dynamical properties, well, it's only one. Okay, let me just now talk about co-quaternion dynamical systems. The origin of this work, everything began in 2012, long time ago already. And the idea was to see if co-quaternionic dynamics were different from complex dynamics, and it's easy to say, but it was very, very difficult at the beginning, but we worked and we could publish the first paper in 2017, and we showed that quadratic co-quaternionic maps had some very, very different properties than the same family of maps in the complex plane. The first property that I would like to remark was that we found non-isolated sets of fixed points and also non-isolated sets of periodic points of period 2. This is very, very in quadratic families of maps. It's very, very different from the complex. And in the same year, we also published a paper where we showed that there is coexistence of attractors for this kind of quadratic maps, for co-quaternionic maps. Something that everyone knows that for complex quadratic dynamics, it's not possible. Well, this year, we could publish some paper now about a different family of maps, of quadratic maps. And this is also something very new in the sense that I was talking about before, in the sense that for co-quaternionic dynamics, we have diversity in the sense that we have properties of for this family of maps, x squared plus B times X that was not found for the first family of quadratic maps, X squared plus C. So this is more or less what we had for the first studies for these two family of co-quaternionic maps, quadratic maps, and the point now is the following. We propose the following problem. We would like to study the stability in the co-quaternionic context of complex attractors. Complex attractors in the following sense. Well, we have complex dynamics, and we found, obviously, we could find the complex attractors, but the idea now is what happened to those attractors if we change the context of the variable, in the sense that we go from the complex plane to the co-quaternionic numbers. And this is the question we studied, and in the following 15 minutes I will give you some answers. Let me just have a remark now. These results are the first step in computing the Mandelbrot step of each family of these families of maps. Well, this is not entirely correct. This is not the first step. This is the second step. Our first step was just experimental. We just computed the Mandelbrot set for the second. We start with the second family of maps we have here, X squared plus B times X. And the first results we got were already communicated in a different conference, and the point was that we were not satisfied with the results obtained, and so we decided to go a little, well, let's say, trying to study some results in a fashion not as experimental as we did. Let me just say a little bit about this Mandelbrot set. Our point was the following. Because we wanted to compare what we were getting with co-quaternion dynamics compared with the complex case. We restrict ourselves with the parameter, a complex parameter. This was let's say, the requirement to compare the results we obtained for co-quaternion dynamics with the complex, everything that we had for complex dynamics. With the first results, we might conclude that maybe this is not the right generalization of the Mandelbrot set, meaning that maybe the Mandelbrot set for this co-quaternionic quadratic maps maybe need a little bit reflection. Maybe we have to think about it a little further in order to obtain something that, in the sense, gives something more related with the diversity and the new things that we got in the first publications. Okay, let's go back to the stability of complex dynamics for co-quaternionic quadratics. I have here some basics for co-quaternions. Let's go. Let me just read the two remarks I have here. And contrary to what happens in the case of Hamiltonian quaternions, H-Coq now it's not a division algebra. This is very, very important for the dynamics. If you think that to compute, to get the fixed point of a map, you have to compute the zero of a polynomial, not with H-Coq, not a division algebra. This is very, very important. Okay, the second remark is the following. This is important for when we are looking for applications, and this is the idea that this is new, that this was known for a long time ago. The algebra of co-quaternions is isomorphic to the algebra of real 2x2 matrices. This is important in the sense that we think it is important in the sense that maybe trying to find some applications of all this dynamics of co-quaternions, maybe it's not as difficult as we might think when we look at all the difficulties of working with this kind of numbers. Okay. The first family of maps, let me put here. We have two theorems. The first one says that the complex fixed point Q is an attractor for the maps for parameter values inside the cardioid with this formula. The second theorem says that the complex two-cycle is an attractor for parameter values inside the circle. Okay, I have here the picture of both regions. The cardioid you can identify at the right and the circle at the left. This is just a joke. It's just for everyone to identify that we are in presence of the cardioid and the first bulb of the Mandelbrot set that everyone knows from the complex dynamics. And I have here a picture of the complex Mandelbrot set. And let me just show you the idea. The conclusion is that the theorem one established that the co-quaternion fixed point, the complex fixed point is an attractor for f at the same parameter values as it was an attractor in the context of complex quadratic polynomials. It is the same for the theorem 2. So now the idea is we have a conjecture. This is not a conjecture. This is it is a conjecture, obviously, but it's a conjecture based on many experimental computations. And I can say that this is very easy because you choose a parameter value and then it is a complex. Okay, the idea is it's very easy. You just choose a parameter, complex parameter, then you iterate zero f from the complex, as everyone knows, and then you have two possibilities. Either you go to an attractor, a complex attractor, because you are with a complex map, or the orbit of zero it does not converges and goes to infinity, and so you have not an attractor for that parameter value. Then the idea is the following. Then you have the complex attractor for that parameter value. You just consider the Quaternion context, and you just check if that complex attractor is also a Quaternion, a complex attractor for the Quaternions. It's very, very easy. So this is a conjecture, but it is something that you can see, not prove, but you can convince yourself. It's very easy to convince yourself that it is true in that sense. Okay, let me just now go to the second family of quadratics. This is, let me just go back. This conjecture says that there is nothing interesting for this family of Quaternion maps. Every complex attractor is also an attractor for the dynamics in the Quaternion context. So it's not a very, very interesting problem. But I must confess that our work was done first for this second family of maps. That's why we were enthusiastic about this problem, and I would say that I would give up if we started with the first family. It was okay. Let me just do the following. The Mandelbrot set for this family of maps, the complex Mandelbrot set, it's not in the literature, so I'm putting here the Mandelbrot set. Please, it's not in the literature for obvious reasons, because this complex family of maps, it's equivalent to the other one, so it's no point to represent the Mandelbrot set. If you think careful, you'll find that we have here two. This is for B belonging to the complexes, the complex plane, and you'll see that we have two families of maps. There are two Mandelbrot sets here. In the following, we will restrict ourselves to parameter values B with the real part larger than 1. Okay. We can say that there are two fixed points. There are two complex points of period 2, and we have one theorem. The theorem 3, it's about it's an attractor. We prove that it's an attractor for the Quaternion map F for parameter values inside the circle. This circle is the large circle we have on the right. Okay, we have a conjecture. The conjecture says that the 2 cycle is an attractor for the Quaternions for parameter B inside a circle. Okay, the circle is the circle here, on the right, the second circle on the right, the big circle over there. Okay, and now, let me just. Now we are going to say something for some bulbs. We have 1 minute. Okay, we have. Let me just show this picture. Okay, this is a zoom of the complex Mandelbrot set, and we are going to say something about these 3 bulbs. The one on the left, we have the B4. B4 because it means that there are a 4-cycle attractor for these parameter values, then B3 and B5. Okay, The first conjecture says the following: for every parameter value inside belonging to the bulb before, the complex force cycle is not an attractor for F, the quaternion maps. Okay, there is nothing new. This is something that we had before. We have the same result, the same conjecture for the bulb 3. Okay, but the idea is that Okay, for bulbs 5, we can say that there is a mixture of stability for the complex force cycle. And we have a picture here. Well, in blue, we have parameter values inside the bulb 5, for which the 5 cycle, the complex 5 cycle, is also an attractor for the quaternion context. And we have here in orange the values of the parameter values for which it's not any longer an attractor. Okay, let me just show you. This is the Mandelbrot complex Mandelbrot set, but here we have in red, orange, let's the parameter values for which the cycle are not attractors. Sorry. Okay. I had a mistake before. Let me just. Okay. This is the end.
Do you have any questions from either the live or the online presence? Okay. So the next two sessions are virtual, and the first talk is the first talk has the name "A Verification of the Domains Tracking Algorithm for Solving the System of Alien-Kahn and Kahn-Hilliard Equations." Dimitri, you're going to present it, right?
Yes.
Okay. Whenever you're ready, you can start. You have something like 20 minutes. And you can share your screen as well. You should actually share your screen. Okay. We can see your screen. You can start. Thank you.
Hello, dear colleagues. My name is Dmitry Prokhorov. I work at the Trofimuk Institute of Petroleum Geology and Geophysics, Siberian branch of Russian Academy of Science. I will present a report about the verification of the domains tracking algorithm for solving the system of Allen-Kahn and Kahn-Hilliard equations. First, I want to explain our interest in this equation system. It is carbon capture and storage, namely the following two problems. The first of them is carbon dioxide absorption by cow-based sorbents, which usually occurs at high temperatures. The second one is the usage of yttrium oxide catalyst support for the process of carbon dioxide methanation, which is also associated with high temperatures. Under the influence of high temperatures, the textural properties of materials change, and the Allen-Kahn and Kahn-Hilliard equation system allows predicting these properties and performing the sintering simulation. Usually, the system is coupled with the phase field method. The key feature of this method is continuous fields describing the shapes and orientation of different grains. Field variables correspond to physical quantities such as density and order parameters C. They take definite values in grains and smoothly changes at the interface. The equations minimize the total free energy, denoted by capital F, where the lowercase f is free local chemical energy density, and beta parameters are the gradient energy coefficients. The second term describes the impact of surface energy, and the third describes the grain boundary energy's impact. Mass density changes under the action of flow J, which is proportional to the gradient of chemical potential mu. Allen-Kahn equation describes the evolution of the order parameters which are related to grains with different crystallographic orientation. The number of the equations equals to the number of grains in the sample. To perform the simulation, equations were discretized with respect to time by an explicit forward Euler rule with step tau. Spatial derivatives were discretized using central finite differences with grid step h for all directions. We parallelized the implementation of the finite difference scheme using CUDA technology for the graphic processing unit. However, the grain growth process occurs during the sintering. The grain sizes are increasing and the grain number is decreasing. Therefore, the initial system if the initial system has not enough grains, we do not obtain the proper result because all grains combine into one. On the other hand, solving the system with a large number of grains requires a huge amount of computational resources. One approach to overcome these difficulties was proposed by Kim and implemented in the PACE3D framework. However, this approach is better for simulating grain growth than for the sintering simulation. Therefore, we developed our approach called the domain tracking algorithm. For each of the Allen-Kahn equations, the solution domain is limited to a small neighborhood of the corresponding grain. During the simulation, the algorithm changes the sizes of locations of domains. The main algorithm parameters are the offset from grain boundary and the frequency of domains resizing. First of all, we performed a common test for sintering simulation. We studied the neck growth behavior, which should satisfy power time dependence, where parameter n depends on dominating diffusion mechanism. The obtained result perfectly fits the parameter expected for grain boundary diffusion. Further experiments are conducted in two variants. In the first of them, the evolution of order parameters is computed in the whole domain without tracking the subdomains. They are denoted with subscript s. For solutions obtained with domain tracking algorithm, subscript a is used. The initial grain structure is 50 equal grains packed by Lobachevsky-Stillinger algorithm. Besides L infinity norm, we use Hausdorff distance normalized by sample diameter for comparison. The Hausdorff distance is computed between sets of nodes of the upscaled grid, allowing the estimation of the interface shift. For most of the simulations, the error in the L infinity norm is less than 100th. Error reaches the maximum value for sample 6 in the middle of the simulation. And this maxima also appears in the graph of error in Hausdorff distance, where the maximal shift of the interface is less than 0.5% of the sample's diameter. Then we studied the algorithm behavior with different parameters for sample 6. Parameters 1 and 2 corresponds to the low offset of the grain boundary, 6 and 7 to the large. Also, the frequencies of resizing are different too. The results show that parameter 1, 2, and 5 have much larger error values than others and are not appropriate for simulation due to the small offset and low frequency of resizing. To better study the difference between the rest of parameters, we introduce another two values for comparison. First of them is the surface area, which is computed using the Monte Carlo method and Crofton formula. And the second one is the Betti numbers, which allow distinguish samples with different topologies. In three-dimensional space, all Betti numbers beginning with the sort A0, the first three present the following characteristics of topological space. B0 is the number of connected components, B1 the number of holes, and B2 is the number of voids inside the space. The sample consists of one connected component and has no void. Also, the samples does not split during the simulation and voids do not appear. Therefore, B0 and B2 equal to 0 constantly. So we present only the B1 graph. At the beginning and at the end of the simulation, the B1 number is equal for all experiments. However, in all experiments except 6 and 7, B1 slightly differs. We assume that evolution of sample structure goes similarly. The cause of discrepancies in graphs are the small changes in the dynamic of pore collapse due to the different parameters of the tracking algorithm. The surface area error has the same behavior as errors defined by the L-infinity norm and Hausdorff distance. The memory usage graph shows that parameters 6 and 7 are not good if computational resources are limited. The following, the previous study allow us to apply the developed algorithm to the study of yttrium oxide specific surface area. The numerical experiments results agree with mercury porosimetry for 900 degrees sintering. However, at 1200 degrees, the grain growth occurs very fast. So there needed to be more grains for the proper simulation. The intrinsic structure of the real and digital samples also agrees at 900 degrees. In total, we have the following results of the work. An algorithm for sintering simulation of granular materials has been developed, and analysis of the parameters influence on the solution's quality and performance was carried out. The algorithm make it possible to perform computations using one NVIDIA Casora accelerator for samples consisting of 8,000 grains, and the specific surface area value obtained from the numerical simulation of sintering agrees with the mercury porosimetry data. Thank you for your attention.
Thank you, Dmitry. I don't know if you heard the clapping from the room.
Yes, I heard.
Okay. Are there any questions here or no? Okay. Yes, there is a question here. Can you please come and, yes, near the microphone?
Okay, thank you for the presentation. Can you hear me, Dmitry?
Yes.
Okay. Thank you for your presentation. I was wondering, for the grains, are you using temperature? Because you had the experimental with 900 in Celsius, right? Do you have such kind of heat equation and do you consider melting of the grains?
Thank you for your question. In these equations, the temperature is in the diffusion coefficient, so it is constant over all simulations. So there are two experiments, one for the first temperature and one for the second. But the melting process occurs. So I want to say that there are no heat equations. The temperature is constant during a single experiment.
Can you please repeat your last sentence? Because we have some trouble hearing you.
I want to say that the model doesn't have heat equation. The temperature is constant in this model.
Temperature is constant. Yeah. Thank you.
Okay, thank you very much. Okay, so now we can proceed to the final presenter for this session. Okay. The next presentation has the title of Accelerating the Simulations of Cardiac Arrhythmia with a Second-Order Numerical Method and High-Performance Computing. And Guilherme, are you ready? Okay.
Yes, hear
You
me,
can
guys?
share your screen. We can hear you.
Okay, let me share.
Yes. Yep.
Can you guys see?
Okay. We can see your screen. You can start. You have 20 minutes.
Okay, so good afternoon, everyone. Good morning here from Brazil. My name is Guilherme Couto. I'm from Federal University of Juiz de Fora, and I will present this work that I did with Noemi Monteiro, Bernardo Rocha, and Rodrigo dos Santos. So this is the agenda that I prepared for this presentation today. I will pass through the background of our work, the methods, the simulation, and some results we achieved. So let's move on first with the context and motivation. First of all, I brought this data here to reinforce the importance of studying the cardiovascular diseases. They are the leading cause of deaths worldwide. So despite of all the technological development of the past years, we still have a huge number of deaths annually. So it's very important for us to convoke other areas of studies like computer science, mathematical, biological, computational engineering for helping to change this scenario. Another interesting data is that of the US, specific for the US, is in 2020, each 4 seconds, a person died of cardiovascular diseases. So this is to show the importance of the time when we are talking about cardiovascular diseases. And here, our work has this goal of accelerating simulations because time is very important. And to move forward, our research, I will locate for you where it is. And this is a diagram that shows how the heart modeling usually works. So first, in the left, we have the patient. With some medical examinations, we can get some data of these patients. And this data, together with some mathematical, physical, biological information and knowledge, we can build a model of a heart, the computational model of a heart. And with this model, we can simulate not in the patient, but in the computational model. And this can improve our diagnosis, our therapies, and the prognostics too. So locating even further our research it is focused here on the computational model. And I think we can expand even further this part in the sequence of 3 parts. First, everything starts with the mathematical model that when we implement, we get the computational model, and with the computational model, we can do simulations and get the results. Our research is located here at the simulation part, where we want to have more accurate results and we want to have more fast simulations. So this is our goal. And now I'll explain what we are trying to simulate. And first of all, our heart, to pump blood for the rest of the body, it has to be stimulated. So the cardiac muscle has to contract in the specific way that the blood will be pumped out. And as you can see here in this GIF, the movement of the heart cannot be random. It has to follow a specific sequence, and the heart, the muscles to contract, they have to be stimulated by a electrical stimulus. The electrical stimulus, when it propagates through the tissue, the cardiac tissue, will generate this movement, and then the blood will pump it out. Here in this graph, you can see that when electrical stimulus goes through a cardiac cell, it generates an action potential that is represented here. In the y-axis here is the potential, electrical potential V, and in this side, we can see a representation of two-dimensional part of the cardiac tissue, where the blue, the darkest areas, represents the regions that were not stimulated yet, and the lighter regions, the yellow regions, represent the parts that were stimulated. So as you can see, the stimulus, when the heart is functioning normally, goes harmonic and with a specific cadence. So here's the function of a normal heart. However, if for different regions, sometimes you can have a premature contraction, and this can break the rhythm of the heart and cause it we call arrhythmia. So the heart stop having that synchronic movement and start to vibrating, which generates in our two-dimensional representation. This is spiral, as you can see over here. This represents an arrhythmia, and this makes that the heart doesn't pump blood anymore, and it's a very serious situation. And this is what we are trying to simulate. Another metric, important metric for studying the arrhythmias, it's called the vulnerability window, and it indicates the time interval where this premature contraction, that is also called extrasystole, induces or not a cardiac arrhythmia. So as you can see here in the left side, if the premature contraction happens before this vulnerability window, it doesn't induce a arrhythmia. If it happens after the vulnerability window, it doesn't induce arrhythmia at all. But if the premature contraction happens during the vulnerability window, you have the spiral and then the arrhythmia representation. So it's a very important metric, and our work simulate this. So, okay, now you know what we are trying to simulate, and then let's describe mathematically what is this. So first of all, we chose Fitzhugh-Nagumo equations to Fitzhugh-Nagumo model to represent the functioning of a cell, a cardiac cell, and we chose the monodomain equation to represent the electrical functioning of the tissue. And as you can see here, when we coupled the Fitzhugh-Nagumo equations to the monodomain equation, it's an adaptive Fitzhugh-Nagumo to represent more specifically the cardiac functioning of the cardiac cells functioning. And when coupled to the monodomain, we get this reaction diffusion system, where in this first variable that indicates the potential, we have this reaction part over here, and then this diffusion part over here, it's a PDE, in our case, for the two-dimensional tissue. And okay, this is our mathematical model, and this is what we are trying to, will solve, and our numerical method is to solve this system. So let's move forward for the numerical method. First of all, we introduced this SSI ADI that comes from for second order semi-implicit, this SSI, and it's based on alternating directions implicit. How it's work? Okay, so we have this first part that we are at time n. I don't know if you can see here, but we 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 split the time step in two parts. In the first half, we have the diffusion implicitly calculated in one direction and explicitly calculated in the other. And the other half, we do the opposite. So it's implicit in one direction and explicit in the other. And this is how the alternating directions implicit works. Here we have the equations that describe what the image shows. So in the first half, we have the diffusion implicitly calculated on x-axis, for example, and explicitly calculated on y. And then the second half, implicitly calculated in y and explicitly calculated in x. This is for the diffusion of the potential. In our case, it's just two-dimensional. And another important part of our method is this predictions calculation. So we have two variables of the Fitzhugh-Nagumo model, and we explicitly calculate two predictions. These predictions will be used in the rest of the method. So we do the predictions for V and for W. This is not the potential in the next step. This will only be used to calculate the potential and here the other variable W. So this is the two equations that is our system of equations that we have to solve in each time step. So we are in time step n, and we want to go to time step n plus 1. And here, as you can see, we have the diffusion, the first half of the diffusion, the second half of the diffusion, and the reaction that is calculated from the predictions I showed previously. And these two equations are our like what we have to solve in each time step. When we rearrange those equations over here, we get something like this for the first half and the second half. And these two equations, when we can write them in the matrix form, and we get something like this. And maybe here is the great insight of this method, because this three-diagonal matrix here, we know a very efficiency way to solve them by the Thomas algorithm. So despite of the expensive iterations the method has, with this we can parallelize it, and we did this, and we can solve it efficiently. So this is a great insight of this method. And now to talk more about the results and we got. First here, in this table, we analyzed the relative error and the execution time. The error, we analyze it comparing to a very small time step, like 0.005. So it's relative of this smaller step, and that is more accurate. And I would like to say that these lines without a number represents that the method got unstable and could not represent the arrhythmias that we were trying to simulate. So for example, for Ford Euler here is a very well-known method, explicit method, and very widely used. And we are comparing our method with the Ford Euler. And as you can see, as we increase the time discretization, the Ford Euler is stopped, got unstable, and didn't represent the simulation we wanted. So I would like to, to highlight two analysis here. First, if we analyze only the execution time, the Ford Euler will outperform the SSI ADI. However, when we saw the relative error here, we can see for the same time discretization of these times, got those errors. So the Ford Euler got an error like more than 2 times the SSI ADI error. And this is the, like, we have to do the choose depending on your application, if you are interested only in time or you want to put the error into your analysis too. Those results I showed here in this table were for the already parallelized execution. We parallelized this code with OpenMP, so in CPU only. And here you can see the error growing for Ford Euler and getting like very small and more stable for the SSI ADI as we increase the time discretization here. And here are a table of the speedups we achieved in this method. The speedups are a very widely used metric to see if the code was good, parallelized or not. And we can get this metric by dividing the execution, the serial execution time for the parallelized one. And in the computer, we run the experiments. We had 6 threads, and those were the speedups we got. So we can got for the SSI ADI almost 4.6 times faster than execution with only 1 thread in the serial execution simulation. So it's a very good speed up. And here for the conclusions, first of all, we can see that the time discretization and choosing a good method is very important to represent the vulnerability of reentry and then studying arrhythmias and so on. And we can see that too, SSI ADI was more stable, accurate, and fast, depending on the application. For example, if your application has has to have a error smaller than 3.5%. Ford Euler takes like 0.639 seconds, while SSI ADI needs only half of this time, almost half of this time. However, if an application is more flexible and can get an error like up to 10%, Ford Euler will outperform SSI ADI, will be faster. And we already have to we until have to test this method with more complex cardiac cells models such as Tentusher or another methods with more equations and more precise representations. And we want to extend this to 3D simulations and parallelize them with GPUs so we can do more realistic simulations. So that was the conclusions. This work is still in progress. And that is, thanks a lot. I would like to thank my university, my laboratory, and the council. And that is, I think I stop.
So, are there any questions? Yes? Come on.
Okay. Good, Herma. Thank you. Great presentation. I really liked it. I was wondering regarding this, the parallelization part. Have you used Python, or from my understanding, is parallelization is done for the solver part, right? For the inversion of that matrix. Am I right?
Oh, yes. No, we didn't use Python. We use C to program. Like C will be more fast to run the simulations. And yes, the parallelized part is only the spatial discretization, not the time discretization, because to parallelize the time, it will be impossible because they have one connection to each other. And yes, it's the calling of the matrix that we parallelize it to solve the matrix.
Yeah. So that's okay. So the tridiagonal matrix. Have you looked to maybe analytical solution of the inverse of the matrix, because this is so structured? Maybe so-called Toeplitz matrix or kind of things. I think might be interesting to look at, and I really like that you parallelized in C++ or C. For the time discretization part, because you have this explicit CFL time limitations, right? That you cannot choose time step, big time step.
Sorry, I couldn't hear the last part.
So delta t, the time step, in order to choose bigger, you have still limitation on your time step, right? CFL, because you have explicit way. Yeah.
Yes.
Wh-
Only the v part, only one of the variables we can have implicitly calculation. So the method is like conditionally stable because yes, it explicitly calculated in time.
Okay. Thank you very much. Good luck. Yeah.
Thank you. Thank you for the tips.
Yeah.
So that's it for the session 3A. Special thanks to all the presenters and the people that were here. Have a nice evening, I could say. Bye. Is there a...
link of the old building of the National University of Athens. There are some directions you can go back. Okay? You will get all the form of
Ipa.